All right, welcome back, everyone. So today we're going to try something slightly different. We're actually going to use technology. So God forbid we use technology. So I wasn't really convinced that all of you in the back could actually see what I was writing the other day, and not to mention the board really sucked at actually erasing. So we're going to try using my iPad instead. So I'm going to write on there, and that's going to project onto the screen. And we'll see how it goes for today. So hopefully it'll work a little bit better so everybody can see a little bit better. And you don't have to do as much screen going up and down as we did last time. So basically just gonna remind you what we talked about last time. So we started talking about harmonic oscillation. So again, harmonic oscillation is anything that repeats itself in a regular pattern unless it's damped, which we'll talk about maybe today, but probably definitely tomorrow. So what we found was what? When it's at its maximum displacement, it had the greatest amount of acceleration, where the maximum amount of acceleration is for the spring mass system, k divided by the mass times the amplitude. But it has zero velocity. When it reaches its equilibrium position, it then has zero acceleration, but it has maximum velocity, where the maximum velocity is the square root of the spring constant divided by the mass times the acceleration. The total energy is constant at all times. That's what this thing says. That's equal to the kinetic energy plus the potential energy. Now, depending on what type of system I'm looking at, for now, we're only looking at the spring mass system. So that potential energy is 1/2 k times x squared, but this will be slightly different also depending on what kind of system I look at, but again, that is just simply equal to a constant. Acceleration at any point is given by negative. Negative, again, just basically means that it's always back to that equilibrium position, so that's the restoring force, k divided by m times the position. Then we said that the position as a function of time was equal to the amplitude times cosine of the angular frequency times time plus phi0, where phi0 again is what we call this phase factor. We'll do some examples with phase factors today so you can kind of get a little bit better understanding of what that is. Again, the phase factor is simply where is it when it starts at time is equal to 0. Does it start off at maximum displacement? Does it start off at the origin? Or does it start off in somewhere in between? That's what the phase factor tells us. The period is related to the angular frequency by 2 pi. And something that we didn't talk about yesterday, but the velocity at which the harmonic oscillator is moving, we can find by taking the first derivative of the position as a function of time. So if we do that, then the velocity as a function of time is a negative the amplitude times that angular frequency times sine of omega t plus the phase factor. So what exactly is this phase factor? So that's the first question we want to ask today. So what is omega? What is this guy? Well, we'll talk about omega. So again, let's bring up our system. So as I say, here's my system. Again, it's harmonically oscillating. This thing is oscillating with some frequency and it's oscillating with some sort of period. Okay? Now this thing is simply oscillating so that it's going up and down, and that's about it. Now what we want to do is compare that to another system that we've seen before, which is uniform circular motion. So here I have this bug. This bug is undergoing uniform circular motion, meaning it has a centrifugal acceleration towards the center, has a tangential velocity, but let's watch what's happened with the bug. So the bug is going in a circle, which means it also has a period, it also has a frequency, but notice if you project the bug directly onto this vertical axis, what does the bug do as a function of time? So meaning if I just stop it at some random point, so let's see if I can stop it. Okay, I want to stop. Reset all. Good. So if I just kind of stop this at some random point, what will happen is this bug will be at some position, and then the angle at which it makes the vertical basically tells me where it is along this vertical axis. Okay, so if I'm going to spin this guy around, spin, spin. There we go. Okay. So again, if I spin this guy around and I compare that to then the spring mass system, which is oscillating up and down, what I can see is they're actually doing the same motion. The spring, as it's oscillating up and down, is only moving here, but the bug, as this guy is actually rotating around, even though he's moving in a circle, but again, if I think about projecting that bug directly onto this vertical axis, the bug is also simply going up and down. So the bug here is also undergoing uniform circular motion, but it's also doing harmonic oscillation. So if I think about shining a light onto the wall over here, and I project the position of the bug, well, the bug is simply only moving up and down. Even though it has an angular velocity because it's moving in a circle, But there's no difference from the motion of the bug than there is to this guy if I project it onto the screen, if I project it onto the wall. So the point of all this is that the angular frequency is actually almost exactly the same thing as the angular velocity. Losing my mask here. Except the bug, all I care about is the projection done onto the screen. Right? If I projected it using some sort of light onto here, I only care about what it's actually doing physically up and down. So ultimately what this tells us then is that the angular frequency is actually almost exactly the same thing as, did you erase everything on it? It did. I hate this thing. Anyways, so projected onto this vertical axis. So again, our question is, what is omega? Well, again, omega is, if I consider something under uniform circular motion, so say here's my object, and here's my object at this point, and I'm going to project this simply onto the y-axis. So here we have some sort of radius. Let's call this A, same thing as the amplitude. Let's call this an angle of theta. What I care about is its position along the y portion, which I'm going to write as x. So actually, let me change this to x. So let's call the vertical axis the x-axis. Okay. So from here, we can then say that what? X of t here is then going to be equal to the amplitude, which is equal to the radius, times cosine of theta, but since this thing is moving with uniform circular motion, omega is equal to a constant, so theta is equal to omega by simply the time. So this tells me then that x of t is actually equal to a times cosine of omega t. So the point of all of this is the fact that the angular frequency tells me about how fast something is moving in a circle. The angular velocity is related to that by simply saying, well, it's the projection of that onto some sort of axis. So either this thing is oscillating straight up and down, or it's oscillating side to side. But it's almost exactly the same thing, which is why it has exactly the same amount of units as well. Now, the point of all this is the fact that I know the acceleration for this guy, uniform circular motion, went as minus omega squared times the radius. So here, my radius was equal to the amplitude. Now, since all I care about, though, is the vertical portion of this, what I can then say is that the vertical portion of the acceleration then is equal to minus the angular frequency squared times then the x position. Notice this acceleration here, which is the y portion of the acceleration for uniform circular motion, is exactly the same acceleration we wrote down for harmonic oscillation, except the only difference here is instead of having a k over m, I have an omega squared. So the point of all this is basically to say that for any physical system, the way we determine the angular frequency for that physical system is to isolate the acceleration. So what you have to do is start off with the sum of the forces, set that equal to the mass times the acceleration, solve for the acceleration. Once you have the acceleration, it'll be something times negative times the position. Whatever shows up in front of that position is the angular frequency squared by definition. Right? So the way you determine the angular frequency, which is exactly related to the angular velocity, is by solving for the acceleration. Once you have that acceleration, whatever shows up in front of x is the angular frequency squared by definition. So if I compare this to my simple harmonic oscillator, what we can see then is that the angular frequency is equal to the square root of k divided by m. So for a spring mass system, the angular frequency is equal to the square root of k over m. This is for a spring mass system. For any other system, well, it's horrible stuff. There we go. All you have to do then is write out the sum of the forces, set that equal to the mass times the acceleration, isolate this for the acceleration, then whatever comes up as omega squared times x, whatever shows up in front of that x is the angular frequency squared by definition. We'll do some examples of this when we do pendulums and things like that, and so you can kind of see it a little bit better. But the angular frequency is defined per system based off of the forces. What's up, Dylan? Oh, a sub y just meant that it was the, oh, sorry, I should have been a sub x, not a sub y. but it just meant that it was the portion of the acceleration along the vertical axis here. That's all that was. Because here, even though this thing is moving in uniform circular motion, the acceleration always looks like this guy in this case. But since I'm only comparing the vertical motion of the bug, so I'm going to bring the bug back up. So if I compare only the vertical motion of the bug, so this bug is simply doing this in the vertical sense. And if I compare that to the spring, which is also only going up and down in that direction, what I care about then is only the vertical projection of the acceleration for that bug. Here I call it x because we called it x before. So I'm just calling the vertical axis x in this case. So yeah, so here, even though this is the actual acceleration, this is only the vertical portion of that acceleration. So that's what ax is. Always okay? So ultimately what this means then is we can go back to our systems before and we can now rewrite these in a general sense. What we had before was that Vmax was equal to the square root of k over m times the amplitude. But I know the square root of k over m is actually equal to omega, so this is actually equal to omega times a. This is the maximum velocity. For the maximum acceleration, we had this was equal to k divided by m times the amplitude, but k over m is actually the angular frequency squared. So this is the same thing as the angular frequency squared times the amplitude. Now the point of this is to make a distinction between the spring mass system and some other harmonic oscillator. Because the angular frequency for the spring mass system, which is the square root of k over m, is completely different than the angular frequency in this case. Or here's a bond, you can see what I'm doing. This is a simple harmonic oscillator. This has nothing to do with the spring. So if I wanted to describe the harmonic oscillation of this thing to talk about its maximum velocity, and I said it was the square root of k over m times the amplitude, that doesn't make sense in this case because there is no k. This thing has no elasticity to it. So this thing simply oscillating back and forth is a harmonic oscillator, but has a completely different angular frequency. But what is true is that that maximum velocity is given by the angular frequency times the amplitude. The maximum acceleration is the angular frequency squared times the amplitude. That's true for any harmonic oscillator. What changes is that angular frequency. So to find that angular frequency, as we talked about here, what you have to do is solve for the forces, set those equal to the mass times the acceleration, isolate the acceleration, get it into a form that looks like this. Whatever shows up in front of x is the angular frequency squared by definition. Is that kind of this? So good. So let's do a couple examples. So the first example we're going to look at is, look at this one. So this says that the displacement of a simple harmonic oscillator is given by x of t is equal to a times cosine of omega t plus phi. And this is for a spring mass system, but actually it doesn't really matter. So in this case, it wants us to determine what is the phase factor given this amount of information. So for part A, what we know is that the position of the oscillator at time is equal to 0 is negative the amplitude. For part B, we know it's equal to 0, so it's at the equilibrium position. For C, we know it's equal to positive the amplitude. For D, it's equal to half of the amplitude. For E, it's equal to negative half of the amplitude. And for F, it's equal to amplitude divided by the square root of 2. So for each one of these, all we wanted to do then is determine what is that phase factor. So to do that, we're going to start off with our general expression. So we have x of t is equal to a times cosine of omega t plus phi 0. Here, what we know is where is it at t is equal to 0. So we're going to say at t is equal to 0, we have x of 0 is then equal to a cosine of omega times 0 plus phi 0. Well, what's anything times 0? 0. So this is actually the same thing then as simply equal to a times cosine of phi 0. So this means that if I want to know the phase factor for each one of these different parts, all I have to do is divide by the amplitude and take an inverse cosine of both sides. So this tells me that my phase factor then is equal to the inverse or cosine of the position at 0 divided by the amplitude. Okay? far, so good. So let's go ahead and do this. So for part A, what do we know? So for part A, we know that x of 0 was equal to, was it negative the amplitude? Positive the amplitude. Negative the amplitude, right? So what this tells me then is that the phase factor is then going to be equal to the inverse cosine of negative the amplitude divided by the amplitude, which is the same thing then as the inverse cosine of -1. So for what angle is cosine equal to -1? So what angle would give me cosine of -1? Remember your trig. 180. 180. Or pi. We're going to work in radians. So this is equal to pi radians. Right. So here, what this says then is it starts off at a negative of the amplitude. So if I plotted this guy, this thing would start off here at negative A and then oscillates like this, which means that this would be a negative cosine curve. This is a negative A cosine of omega t. So remember, pi in this case is going to bring it to a negative value. So part B, here we know that the initial position is equal to 0. It's at its origin. So here this tells me that the phase factor then is going to be equal to the inverse cosine of 0 divided by the amplitude, which is the same thing as the inverse cosine of 0. So for what angle is cosine equal to 0? So what angle is cosine equal to 0? 90 or 270, right? So this is equal to plus or minus pi over 2. So what's the difference between those two? Well, here, again, if I plotted versus time, x. So if it was positive pi over 2, then I would have a sine curve, so it would look simply like this. This would be with the positive sign. If I had a negative, it would actually do this. This would be the negative. Right? That's the difference between the two. Okay? Part C, we now have that the position as a function of time at the initial time is equal to the amplitude. So here we then have that what? The phase factor is equal to the inverse cosine of 1. For what angle is cosine equal to 1? 0 or 360 or 2 pi. Good. Here I'm just going to write down 0. So this is then simply equal to 0. So this tells me if I plotted this one, this would then just be a regular cosine curve. We would just do that. Start off at the amplitude. So there'd be no shift. Part D. So part D, we now wanted to know when it was equal to half of the amplitude. So now we have x of 0 is equal to a divided by 2, which means the phase factor then is equal to the inverse cosine of 1/2. So does anybody know where cosine is equal to 1/2? So what angle is it equal to 1/2? 3 pi over 2?
Oh, sorry.
Pi over 3, good. And that's what, 60 degrees, right? So this is going to be equal to plus or minus pi over 3. Or in degrees, this is then plus or minus 60 degrees. Part E, this was now equal to what? Negative. So we have x of 0 then is equal to negative a over 2, which means the phase factor then is equal to inverse cosine of negative of 1/2. Where's this guy equal to negative of 1/2? Basically, let's put a 2 pi in front, just a 2 in front. So here, this tells me that my phase factor then is equal to plus or minus 2 pi over 3. Finally, last one, F. Here we have x of 0 was equal to the amplitude divided by the square root of 2, which means that our phase factor then is equal to the inverse cosine of 1 over the square root of 2. For what angle is cosine equal to 1 over the square root of 2 or square root of 2 over 2? That's the same thing. So what angle is that one? Yeah, so pi over 4, I'm just going to write it as negative 3 pi over 4. Good. So this is then equal to plus or minus pi over 4, so 45 degrees. So again, this is the phase factor. Now, what the phase factor again tells me is how does my system start at t is equal to 0? So if I go back to some of these ones that we actually plotted, you can see that a little bit better. So here, this one's telling me it starts off as a negative cosine. This one tells me it starts off as either a sine or a negative sine. This one tells me it starts off as a cosine, and then again, there's something in between. Now, the other thing to take away from this is notice that for A and for C, there was one answer. For all of the other ones, though, there are 2 answers. The question is, why is there 2 answers instead of A and C, which there's only 1 answer? So why isn't it sufficient, or say part B here, for me to only tell you the position, but not tell you anything else? So why is that not sufficient? So again, if I look at my plot here, so my plot says that both of these two start off at 0. But what's the difference between the +1 and the -1? For the +1, what's the direction that the harmonic oscillator is moving? Say upward. For the -1, what's the direction the harmonic oscillator is moving? Downward. So the other point of all this is to tell you that just because I know where it is at time is equal to 0 is not enough information to fully specify what this thing is actually doing. To fully specify what my harmonic oscillator is actually doing as a function of time, I have to know 2 pieces of information. I have to know where it is at time is equal to 0, and I need to know how fast is it going at time is equal to 0. So ultimately, all of this tells me then that we need 2 pieces of information to fully specify the motion. Those 2 pieces are, I need to know where is it at t is equal to 0, and I need to know how fast is it going at t is equal to 0. These 2 pieces of information together will fully specify what my system is doing. Because just because it's at the origin doesn't tell me is it moving up or is it moving down. What's the difference? If it's moving up, it's a positive sign. If it's moving down, it's a negative sign. I need to know both of those pieces of information, which means that to fully specify the phase angle, this is then equal to the inverse tangent of then the negative of the position at time is equal to 0 divided by the velocity times the time at t is equal to 0. These 2 things have to be true. Once I know these, then I can fully specify the motion. Oops. Sorry about that. I got those backwards. Should be V0 here, X0 here. Sorry about that. There we go. And my units didn't look right. So once I know its position and its velocity at time is equal to 0, then I can fully actually specify what that is. Now again, once I know what the angular frequency, or in this case the phase factor is, that stays fixed over all times. That is a constant. That thing never shifts. The only thing that is telling me is how do I change my cosine curve? Does it move to the right? Does it move to the left? Does it move a little bit to the right? Does it move a little bit to the left? What is this thing actually doing? Once I know that, I can fully specify my system and then move on from there. Is okay? Let's do another example. So the next example says, oops, wrong one. Oh. So this one says that at time is equal to 0, we have a mass of 0.65 kilograms, that's this guy, is initially at rest at the end of a spring, where the spring constant of the spring is 184 newtons per meter. I see it sitting there, I don't like that, I get pissed off at it, so I hit it with a hammer. Why not? So I'm going to swing this hammer. I'm going to hit the hammer, giving it then an initial velocity of v0, where that initial velocity is then 2.26 meters per second. From here, we want to then determine what's the period, what is the frequency, what's the amplitude, what is the maximum acceleration, what is the position as a function of time, what is the total energy, and then what is its kinetic energy when this thing is at 0.4 times the amplitude. So these are all the things that we want to know. So again, scenario, this thing is at the origin, so this position here is the origin. And hit it with a hammer, it's still at the origin, but now it starts to move in this direction with a velocity of 2.26 meters per second. From there, I want to know all of these other things. So let's do that. So, question number 2. So let's kind of quickly redraw. So here it is. It's at x is equal to 0, given an initial velocity v0, which is equal to 2.26 meters per second. This thing has a spring. The spring constant is 184 newtons per meter. Part A, we want to know what is the period and what is the frequency. Okay? So good. So let's talk about what we know. What we know is that the period is related to the angular frequency by 2 pi. What else do we know? Well, we know it's a spring mass system, so we know that the angular frequency for the spring mass system is square root of the spring constant divided by the mass, where the mass is equal to 0.65 kilograms. So from here, we can then say that the period is going to be 2 pi times the square root of the mass divided by the spring constant. Okay? Plug in my numbers. What I get then is that the period is equal to 0.37 seconds. For the second part, we then want to know what's the frequency. Well, we know the frequency by definition is the inverse of the period. Or it's equal to the angular frequency divided by 2 pi. Either one. Here, since I know the period, then I can invert this, and then that works out to be 2.7 hertz. Remember from last semester, frequency has units of hertz, which is per second. Is okay? Not too bad, right? Good. Part B. Part B, we now want to know what then is the maximum velocity. Well, we now know that Vmax is equal to, actually, no, what do we want? We want the amplitude, sorry. So here we want to know what is the amplitude. So what is the amplitude of oscillation? So this thing is going to harmonically oscillate back and forth, where it's going to reach some sort of maximum position, which is then the amplitude. So we want to know then what is the amplitude. So what is that maximum distance that this thing is going to reach? So how would I do this part? How would we then determine what is the maximum displacement this guy is going to make it? And I'll give you a hint. I started writing it down. What's up, Grant?
You just use the Vmax equal to square root of J over M times A.
Good. So here, we're going to use that Vmax is equal to the angular frequency times the amplitude. Good. So the angular amplitude then is equal to the maximum velocity divided by omega. So why would I do that, Grant?
When you solve for your Vmax, you just simply solve for amplitude. You already have omega.
Well, good. So let's go back to Vmax. Do I know Vmax?
No, but I think we have a formula for it.
Molly's shaking her head. How are you shaking your head? We have Vmax, right? The initial velocity at which I gave this guy, this 2.26 meters per second, is actually the maximum velocity. Why? Molly, go for it. Not at its amplitude, but at its origin, at its equilibrium, right? What we know is that for any harmonic oscillator, when it's at its origin, it has to have the greatest amount of velocity because it has zero acceleration. That is the fastest that this thing is going to reach. Here, this thing started off at the origin with an initial velocity of 2.26 meters per second, which means that 2.26 meters per second, which is the initial velocity, is its maximum velocity. That's the fastest that that thing is going to reach. So here, we actually already know Vmax. We just have to identify that the initial velocity actually is Vmax in this case. So this is actually the same thing then as the initial velocity divided by the angular frequency. So look at my values. What I get in this case then is this works out to be 0.13 meters. So this is its amplitude of oscillation. What's that? Oh, W in this case, remember, is equal to the square root of K over M. So just plugging in numbers that I had. So another way to write this is this would be equal to, amplitude then would be equal to V0 times the square root of M over K. Good. Part C, we want to know what is the maximum acceleration. So what's the maximum acceleration that this guy reaches? So did we talk about maximum accelerations? Yes. What's the expression for that? Well, in general terms, that's equal to the angular frequency squared times the amplitude. So in this case, it's going to be equal to K divided by M times the amplitude. Plug in my numbers. What I find in this case then is this works out to be 36.8 meters per second. Okay? Part D. Part D, we then want to know what is then the position as a function of time. Well, we know the position as a function of time is equal to the amplitude times cosine of omega t plus phi0. Okay. Now, technically, in this case, we would have to determine what is the phase angle, right? Which we can do by using that phase angle that I wrote down, which is the inverse tangent of blah, 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 right? But in this case, we don't actually have to do that. Why don't we have to do that? Where does my harmonic oscillator start? At the origin. It's moving to the right, which we can call the positive direction. So meaning if I plot this thing as a function of time, is that going to be a positive sine curve or a negative sine curve? It's simply a positive sine curve. So in this case, we already know the phase factor. The phase factor can actually go away, and we can actually rewrite this then as A times sine of omega t. And again, the reason for this is that it starts at the origin. At x is equal to 0, and its velocity is increasing, so it's moving to the right. So here we know the amplitude is equal to 0.13 meters times sine of omega, which is the square root of K divided by M times the time. Plug in those numbers, that's going to be 0.13 times the, or 0.13 meters times that is sine of, if I plug in my numbers, this works out to be 16.82 radians per second times time. So everything that shows up in here always has to be radians. So for this section of the course, make sure that your calculator's in radian mode, not degree mode, because otherwise that's going to give you the wrong answer. So make sure it's in radians and not degrees. Good. Part E. Part E, we're now looking for the total energy. Now, we talked about yesterday, the total energy is either going to be equal to the maximum kinetic energy, or it's equal to the maximum potential energy. For the maximum kinetic energy, this is 1/2 the mass times the maximum velocity squared, or this is 1/2 the spring constant times the amplitude squared. Either one of these is fine. Now, for those of you who had me before, I would talk about using the first one, because here we're not using any calculated numbers. We know the mass, we know the maximum velocity, that's just the initial velocity. So here there's no calculated numbers. Here we know this, but this we calculated. So if I use the calculated number, it could end up being wrong if I calculated it. But either way, it doesn't really matter. This works out to be 1.7 joules. So that is the total kinetic energy. Finally, part F. So part F then says that we want to know what is the kinetic energy equal to when my oscillator is at a position of 0.4 times the amplitude. So I want to know simply how much kinetic energy does this thing have when it's at 0.4 times its amplitude. So let's kind of draw how quickly it's going on. So again, here's my mass, moving initially with V initial. Amplitude is somewhere out here, so this is going to be my amplitude. So what's happening then is that my oscillator is about here, moving with some velocity V, which means that it has some kinetic energy K. So what I want to know is when it's at this point here, which is at 0.4 times the amplitude, how much kinetic energy does this thing have at this point? So how would I do this part? How would I do this guy? So what should I use here? Give me a hint. What's true about the total energy? Is it changing or is it constant? It's constant. So here, the easiest thing to use is actually conservation of energy. So we know the total kinetic energy, or the total energy, is equal to the kinetic energy plus the potential energy. Here, we know the potential energy because we know where it is. We know the total energy, that's what we just calculated in the previous part. The only thing we don't know is then the kinetic energy. So from here, the kinetic energy then is simply equal to the total energy minus then the potential energy. So this is going to be equal to the total energy minus 1/2 K times the position that's at squared. So I know the total energy, this is simply equal to 1.7. I know the position, that's then 0.4 times the amplitude. Plug in our numbers, what we find is that this works out to be 1.45 joules. So at this point, actually, most of the energy is in kinetic energy. What's up, Dylan?
So for the X, are you
Yep.
getting 0.4
Times 0.13. Yep. Yep. Yeah, because the amplitude in this case is 0.13 meters. So yeah, so it's 0.4 times 0.13 meters. Okay. Let's do one more example. This one's mostly inserted to get your brain to remember things. So what this says is that in this figure here, we have mass M1, which has a mass of 0.2 kilograms, is sliding to the right on a frictionless surface, which is elevated above the ground here. So imagine this is a table, which is then, 4.9 meters above the ground. So this is a flat, frictionless, horizontal table. And M1 here is moving to the right at 8 meters per second. The spring constant, so M2 is attached to a spring, which is attached to a wall, where the spring constant is equal to 1,208.5 newtons per meter. So what's going to happen then is M1 makes a one-dimensional, perfectly elastic collision with M2, causing M1 to move back in this direction with a new velocity V1 prime, which then causes M2 to start to move with an initial velocity in this direction, which causes it to undergo harmonic oscillation. So M2 is going to harmonically oscillate back and forth. M1 is going to fly off in this direction. Okay. So from here, what we want to know then is, if this thing has a period of oscillation of 0.14 seconds, what is the mass of M2? That's the first thing we want to know. Then we want to know how fast is M1 moving to the left here after the collision. Then we want to know, after it flies off the side, it undergoes parabolic motion, projectile motion, to which it's going to land on the ground, and I want to know how far away from the bottom of the table does it land. So here we're bringing up old ideas, conservation of momentum, projectile motion, kinematics, all that good stuff, because we're going to need all that stuff throughout the rest of the semester. So one thing about this class that's very important, don't think you can forget about anything from 205. All of that stuff will haunt you for the rest of the semester. That's why we're doing problems like this, trying to get you to remember all those things. So this class is a little bit difficult because you have to remember everything from 205 and everything from 206 on top of that. So just because we're done with 205 doesn't mean it goes well. And again, all of you are pretty much engineers, so 205 will never ever go away and throughout the rest of your life. Okay, so remember that. So good, so let's talk about this problem. So good, so first thing we want to know is what is the mass of this guy? Second thing we want to know is how fast is this thing moving to the left? Last thing we want to know is how far does this guy go under parabolic motion? So let's do all that. Good, so part A. So again, initially what I have is m1 moving in this direction. The initial velocity v0, which is equal to 8 meters per second. This is going to hit m2, which is initially stationary. So this is going to be x is 0 is equal to 0. Initial velocity v2 is equal to 0. And this is attached to a spring. So this is my before picture. Afterward, we're now going to have m1 moving in this direction with a velocity of v1 prime. So we want to know what that guy is. We call that v1 instead of the initial. And then m2 is going to be harmonically oscillating back and forth with a period equal to 0.14 seconds. So the first thing I want to know is, what is m2? So how are we going to solve for what m2 is? So this is about the only new stuff from this semester that we have in this problem. Everything else is old stuff. So how would we determine m2 in this case? What do you think? Well, let's think about what we know. Do we know its period? Yes. So let's think about period. So we know period is equal to 2 pi divided by the angular frequency. What type of system is this? It's a spring mass system. So we know the angular frequency is equal to the square root of the spring constant divided by the mass. Do we know the spring constant? Yes. Which mass is this? So which mass is actually oscillating? Is it m1? Is it m2? Or is it m1 plus m2 because it's the total mass? So which one do we think? So which mass is important? So is it m1, m2, or m1 plus m2? Those are basically our three choices. What do you think? What do you think, Clayton? Sure. Well, that's a good question, because that answers actually what mass it is. So, is the period only given by when these two things are stuck together, in which case it would be the two masses, m1 and m2, or does the period have basically nothing to do with m1 because it's only m2 which is oscillating back and forth? It's only m2, that's right. Because what's happening is only m2 is oscillating back and forth, so it's only m2's mass that matters. m1 and m2 together matter for the initial velocity under conservation of momentum, but after m1 comes off, only m2 is oscillating, so the only mass that matters is m2. Cool. So here, the only mass that we care about is m2. That's it. Once I understand that, then I can do everything else. So from here, let's plug this in here. So it's going to be equal to 2 times pi times the square root of m2 divided by k. So good. From here, what I want is m2. So I'm going to divide both sides by 2 pi, square to get rid of the square roots. So ultimately what I'm going to have then is, let's switch to another page. So I get m2 then is equal to 4 times pi, oops, sorry. That needs to be on the bottom. So this is going to be k divided by 4 times pi squared times the period squared. So this is M2. Good. Plug in my numbers. What I find in this case then is M2 is going to be 0.6 kilograms, which is bigger than M1. Part B now we want to do conservation of momentum. So in this case, all we care about is V1 prime. So if you go back to last semester, what you can do is you can look up the fact that for a one-dimensional elastic collision, the most general expression then is equal to V1 times M1 minus M2 divided by M1 plus M2 plus twice of M2 times V2 divided by M1 plus M2. Yeah, if you don't have this memorized, don't worry about it. You can look it up at some point. Now here, what we know is that this is the initial velocity of V2. V2 is initially not moving, which means this whole entire second term is gone because V2 initial is actually equal to 0, so that term is gone. Which means we're stuck then with only the first term. Plug in my numbers, what I find in this case then is it is negative 4 meters per second. So this is the speed at which this guy is moving after the collision. Part C, so let's talk about part C. So what's happening now is M1 is here, moving now in this direction with a velocity of V1 prime, which we now know is 4 meters per second. The negative just means it's moving opposite direction originally moving. Then it's going to fall off this cliff here, where it's going to fall down a distance of h, which was equal to 4.9 meters, undergo projectile motion, meaning this thing is going to do one of these, and then land on the ground down here. M1. What we want to know is what is this distance of t? So here we have to do projectile motion. So if we go back in our memory banks and we remember how to do projectile motion, remember for projectile motion we had to work with both the x direction and the y direction simultaneously. So here we had to write down the x component and we had to write down the y component. For the x component we had x was equal to x naught plus v naught times t. Remember, there was no acceleration in the x direction, so let's ignore that. And then we have y that is equal to y naught plus the initial y times t plus 1/2 the acceleration in the y times t squared. Now, whenever we talk about projectile motion, what's the first thing we always have to do? So think it way back when. Projectile motion, what was the first thing we always had to do? Draw a picture. What was the second thing we did? Put in a coordinate system. Okay? None of these things have any meaning until we put in a coordinate system. So let's decide a coordinate system. As you guys remember, I'm married, so I let women run my life because that's what they do, especially my daughter. She's a little tyrant. So anyways, I'll let one of the ladies here decide what I'm going to do in my life. So Caitlin, why don't you tell me the coordinate system you want to use? Now, okay, coordinate systems, there is no wrong choice. So don't feel like you're overly pressured. Just choose something. Where do you want your origin to be? Most logical places are either take it here or here. So which one do you want to do? You want to take it at the bottom or at the top? The top? Okay. So let's choose. I'm going to have a little bit of free will here. I'm going to choose x in this direction. Now you're going to tell me which direction you want y. You want y to be going upward positively or downward positively? Downward, good. So let's choose that coordinate system. So y, then we're going this way. So according to this coordinate system, then that means y is simply g, and it's positive because it's pointing downward, and we're going downward. So from here, we know that what? There is no initial velocity in the y direction because it's only coming off horizontally. We know this guy is going to be a positive with a g. Caitlin chose that both x0 and y0 were both equal to 0, so that's good. So let's rewrite. So this is then going to be equal to the initial, or actually in this case, which is v1 prime times the time, which is then equal to, on this guy, simply 1/2 gt squared. Now, remember projectile motion, we have to use the y direction in this case to solve for the time. Because we know everything in the y direction, we then substitute that into the x direction to find the distance it goes in x. Okay. So here, we just have to simply use the fact that it hits the ground when y is equal to h. follows that total distance of h. From here, we can find the time. The time then is going to be equal to the square root of twice of h divided by the g. Take that, plug it in here. So this then says the distance d is going to be v1 prime times the square root of 2h divided by g. Plug in my numbers. What I find in this case then is, for part C, the distance at which it falls or lands away from the base is equal to 4 meters. Reason for that is the time is 1 second. So I'm going to plug that in as 1 second. Because this is 4.9 times 2, which is 9.8. 9.8 divided by 9.8 is 1. Square root of 1 is 1. 1 times 4 is good. Okay? So harmonic oscillation. So what we're going to start doing then tomorrow is move on and start talking about other types of harmonic oscillations, which is damped harmonic oscillators, and we'll move into spring or simple pendulums and physical pendulums and all that kind of good stuff. Right? So as I said, a lot of these problems are mostly to kind of get rid of the cobwebs for things that we did in the past, because you are going to definitely need all of those things, especially conservation of energy, kinematics, all that good stuff. So have a good night. I'll see everybody tomorrow. So what do you think? Was writing on the tablet better?
Yes.
Yeah. Okay. We'll do that from now on. I'll be right back. I recorded it, so I could. Yep.
How do you know you sign?
Oh, because our system starts off at the origin. So because it starts off at the origin, we know it has to be a sine wave. The sine starts off at x is equal to 0. Now, the only question is if it's a positive sign or a negative sign, but we said because it's moving to the right, we're taking right as positive, so it's a positive sign. Otherwise, I could also come with that by basically using that inverse tangent stuff. But we didn't need to do that because we know it starts off the origin, so it has to be a sine.
Okay, thank you.
Sounds good? What's up, Nathan?
I am able to see this a lot better, but I think there's one downside. You have less room, so you switch pages faster.
Gotcha.
Sometimes I miss what you're writing.
Okay, I'll keep that in mind. The good thing is I did record this, so I can throw it up on YouTube so everybody can watch it. The only problem with that, though, is I think what's going to happen is half the screen will be me, and the other half is going to be Vanya staring, looking confused, probably. So, but hopefully not confused. So it should be good. Okay. What's up?
For the questions that you're using for the examples, are those posted anywhere, or is it?
No, those are usually just stuff that I'm just kind of using. So, yeah. But again, I should be posting this video because some people asked to do it. So as long as I'm using the laptop and I'm recording, and I can always just post it up so you can go, through those problems again.
Awesome. Thank you very much.
You're welcome. You too. Thank you. So, any questions or anything?
No, that looked a lot better. Like on my end, like I could see it a lot better.
Good.
Yeah, but like they said, like the examples, like I didn't have time to like write them all down before. So